In this video, I will solve the Schrodinger equation for the three-dimensional rotation by converting the x, y, z Cartesian coordinates to the r, theta, phi spherical polar coordinates. The time-independent Schrodinger equation is h psi equals E psi. H is the Hamiltonian. H equals the potential energy operator plus the kinetic energy operator. The three-dimensional one-particle rigid rotor is also called particle on a sphere. We assume the radius of the rotor is a constant r0. Therefore, the Schrodinger equation is this. We have the kinetic energy operator in the x, y, and z direction. We have the potential energy here, and h psi equals E psi. Note this potential energy is 0 when r equals the constant r0. The potential energy is infinity when r is different from the constant r0. Over here, it shows you the position of the particle. Can be expressed by x, y, z, or r, theta, and phi. R is the distance between the particle and the center of the coordinates. Theta is the angle between the z-axis and the vector r. This phi is the angle between the x-axis and the projection of this r onto the xy plane. The conversion from the xyz Cartesian coordinates to r, theta, phi spherical polar coordinates is straightforward. So first, the projection here is r0 times sine theta. Therefore, x equals r0 times sine theta times cosine phi. And y equals r0 times sine theta times sine phi. And z equals this r0 times cosine theta. The conversion from r, theta, phi spherical polar coordinates to the x, y, z Cartesian coordinates is also easy. R equals the square root of x squared plus y squared plus z squared. And tangent theta, theta is here. This tangent theta equals this distance between this position of the particle and the z-axis over here, which is the square root of x squared plus y squared divided by z. So it's here. And over here, how phi is determined? Phi is simply the arctangent of y over x, or tangent phi equals y over x. What about the range of theta and phi? Phi is from 0 to pi, so we can see this here. Phi is from 0 when r is in the z-axis, theta is 0. And it can be pi when r is pointing to the opposite direction of z. So it's from 0 to pi. It corresponds to the latitude of Earth. How about phi? Phi is from 0 to 2 pi. So we can have this phi rotating about the z-axis 360 degrees. Phi corresponds to the longitude of Earth. And again, if we try to determine the value of phi, we need to know the signs of x and y. If both x and y are positive, phi is between 0 and 1/2 of pi. We now derive the Schrodinger equation in spherical polar coordinates. This is the Schrodinger equation in x, y, z Cartesian coordinates. And then, using the chain rule, we have delta psi, the wave function psi, over delta x, when we hold y and z constant, is equal to the sum of three terms. This is because when you change x, you change r. When you change x, you change theta. When you change x, you change phi. So x is a function of r, theta, and phi. Therefore, we have three components. The first component tells you when x changes, r changes. When r changes, psi changes. The second component tells you when x changes, theta changes. When theta changes, psi changes. The third component tells you when x changes, phi changes. When phi changes, psi changes. Fortunately, this is a rigid rotor, so r is a constant, r naught. Therefore, we can delete this term. There are only two terms left. And similarly, we have delta psi over delta y. And again, when y changes, psi change. When psi changes, when y changes, theta changes. When theta changes, psi changes. Also, when y changes, phi changes. When phi changes, psi changes. So therefore, we have another first derivative, delta psi over delta y, being expressed as delta psi over delta theta and delta psi over delta phi. Finally, z is r naught times cosine theta. So it is just a function of one single variable theta. Therefore, we have only one term here. And when z changes, theta changes. When theta changes, psi changes. We'll look at the simplest delta psi over delta z here. So over here. And then it's the product of two terms. It's very difficult to evaluate delta theta over delta z directly. So we use a trick here. We do delta tangent theta over delta z. This is doable. And then we do this d theta over d tangent theta, or the reciprocal of d tangent theta over d theta. So this part is simply the reciprocal of the first derivative of tangent theta, which is 1 over cosine theta squared. Why can we do this? This is because tangent theta is simply the square root of x squared plus y squared. Remember, this is the projection of the r vector on the xy plane over z. And then we can do this easily. Over here, again, you can see x and y are held constant. So really, we're just looking at this term, the square root of x squared plus y squared times the first derivative of 1 over z. And that's just negative 1 over z squared. So we have this term here. And this becomes cosine theta squared. And then we plug in the expression of x, y, and z in terms of r, theta, and phi. And we have this expression here. We simplify this whole expression. We get negative sine theta over r naught times delta psi over delta theta. So this is simply the first derivative of psi with respect to z. How do we get the second derivative? Very simple. We just apply the same operator twice. What operator? This operator. Negative sine theta over r naught times delta over delta theta. That's our operator by holding r and phi constant. So we're going to do this here, the second derivative. Again, we're doing this. Negative sine theta r naught squared delta over delta theta. Negative sine theta over r naught delta over delta theta. We apply this same operator twice to the wave function psi. The two negative signs cancel, so we don't have negative sign here. R naught is a constant, so we took it out. And then inside, we just evaluate the first derivative of sine theta times the first derivative of psi. We use the product rule. The first derivative of sine theta is cosine theta. So we got this here. And then we copy sine theta here, and then we take the first derivative of the first derivative. We get second derivative. And we then clean it up. We have 1 over r naught squared times this everything inside the square brackets. That's the second derivative of psi with respect to z. What about this second derivative of psi with respect to x and y? They're much more tedious. It's not too complicated. It's not too difficult, but it's very tedious. So I'll skip this and this derivation here. And if you're interested, I will post some supplemental information about deriving this too. Now, assuming we got this to convert it into the r theta phi spherical coordinates, and then the Schrodinger equation becomes this: negative h bar squared over 2i, where I is the moment of inertia, I is m times r naught squared for the free rotation of just one particle, and then inside this square brackets, it's 1 over sine theta delta over delta theta, and then sine theta times delta over delta theta, and then plus 1 over sine theta squared. Over here, that's the second derivative of phi. We apply this whole operator to the wave function, we get E psi. For a two-particle system, we just need to do one thing. This moment of inertia is now mu times r squared, where mu is the reduced mass. 1 over mu equals 1 over the mass of particle 1 plus 1 over the mass of particle 2. If we solve this Schrodinger equation, we'll get an infinite number of eigenfunctions, and the eigenfunctions depends on two quantum numbers, L and m sub L. So we put L here in the subscript. I put m sub L here in the superscript. And it's a function of theta and phi. All right, and m sub L can be from negative L to positive L. Why do we use these notations? Remember, in general chemistry, when we talk about the angular momentum of electrons and its z component, we used L and m sub L as the corresponding quantum numbers. So what are the functions here? So again, this eigenfunction y is a function of theta and phi. And then the form, the expression of the function, depends on two quantum numbers, L and m sub L. When L is 0, m sub L can only be 0. What's the function? It's a constant. That means this function does not depend on theta or phi. It's a spherical function. Now, the second function, L equals 1, m sub L equals 0. And you get this cosine theta times a constant. So really, what's cosine theta? Cosine theta is z over r naught. So really, you are looking at something similar to the 2pz orbital. And over here, y1 sub 1, y is the value of L, plus minus 1. That's the value of m sub L. You get this function, sine theta, times e to the power plus minus I phi. This is a complex function. This complex function is a linear combination of cosine phi and sine phi. So overall, here is the linear combination of x and y divided by r naught. So really, these two functions are simply the 2px and 2py atomic orbitals. And then we have d orbitals. This corresponds to the dz squared orbital in general chemistry. And over here, this is simply 3z squared minus r naught squared divided by r naught squared. So you can tell by looking at this, there are two nodal surfaces when cosine theta equals plus minus 1 over the square root of 3. Over here, we're looking at the linear combination of dyz and dxc. Over here, we're looking at the linear combination of dxy and dx squared minus y squared. So you can expand this e to the power of plus minus 2I phi, and then you will see this function is simply x squared minus y squared divided by r naught squared, or x times y divided by r naught squared. So let's look at the shapes of these eigenfunctions. When L equals 0, 1, 2, and 3, okay, we'll see this kind of shapes. When L equals 0, we see a spherical shape. It's just the s orbital. When L equals 1, m sub L can be negative 1, 0, and 1. And then we actually do linear combination for the three eigenfunctions when L equals 1. We got the three different orbitals. They correspond to px, py, and pz. What about L equals 2? When L equals 2, we have 5 d orbitals. They look like this. How about L equals 3? You'll get 7. They look like f orbitals. And what about the corresponding eigenvalues? That's very simple. The eigenvalues are L times L plus 1 times h bar squared over 2I. I is the moment of inertia. So this is the three-dimensional rotational energy of the free particle on the sphere. And L can be 0, 1, 2, and 3, and so forth. So what about the angular momentum? Well, it's very simple. Because the rotational energy is the angular momentum squared over 2I, therefore this part on top is the angular momentum squared. Therefore, the magnitude of the angular momentum is the square root of L times L plus 1, and then times h bar. What about the z component of the rotational energy? It's also simple. It's ml squared, h bar squared over 2I. And m sub l can be negative L plus 1, and so forth until m sub l equals L. So it's from negative L to L. What about the angular momentum in the z direction? It's m sub l times h bar. Remember, this m sub l can be from negative L to positive L. So there's a degeneracy of 2L plus 1. Right? Oh, and how do you memorize this rotation energy? It's pretty simple. You have a common factor here. H bar squared over 2I, that's the common factor. H bar squared over 2I is the common factor. For the three-dimensional rotational energy, it's L times L plus 1, and then times H bar squared over 2I. And over here, this is just the z component. And then you have m sub L squared. Remember, m sub L squared is always smaller than L times L plus 1. That makes sense. The z component of the rotational energy is always smaller than the total rotational energy in all three dimensions. Now let's look at one specific example. So this is just one of the eigenfunctions. L equals 1, m sub L equals 0. It's a function of theta and phi, but of course in here there's no phi. It's just a constant times cosine theta. What about the constant? This is just the normalization factor. This ensures that the squared, if you integrate the squared modulus of this function, you get 1. Now we apply the rotational energy operator to this wave function. And over here, that's the rotational energy operator. We got this by converting the x, y, z Cartesian coordinates to r theta and phi coordinates. And then we just apply this operator to the eigenfunction. The result is very simple. It's h bar squared over I times the original wave function. And we can double check. We can write out the expression of the rotational energy and plug in L equals 1. When L equals 1, the result is h bar squared over I. So we got the same result. And because the rotational energy equals the angular momentum over 2I, therefore we get the magnitude of the angular momentum, which is 1 bar, or which is 1 h bar, or L h bar, where L is 1. Now let's look at the z component. So we apply the operator of the angular momentum in the z direction to the wave function. So what is this operator? It's this. In short, it's the x position operator times the py operator minus y operator times the px operator, in which px and py are the momentum operators in the x and y directions. And then we apply this operator to the wave function here. The result is 0 h bar. That means the angular momentum in the z direction is simply 0. The particle does not rotate about the z-axis. So the rotational energy of the particle resides in the x and y directions. And over here we know this m sub L must be 0, and over here we see m sub L is indeed 0. Okay? And recall the definitions of the angular quantum momentum L. It's also called as the Muthel quantum number L, and the magnetic quantum number m sub L in general chemistry. So this m sub L is simply the z component of this L three-dimensional vector. So now you know where this L and ml come from. They come from quantum chemistry. They come from the solving Schrodinger equation for the three-dimensional rotation on a sphere. And by convention, L is used for electrons, and m sub L is used for the z component of the angular momentum of the electrons. What about the rotation of molecules? When we have a molecule such as a hydrogen molecule or HCl molecule, we use a different notation. J is used instead of L for the quantum number of the three-dimensional rotation of a molecule. We got this rotation energy equals J times J plus 1 times h bar squared over 2I for a linear molecule, and I is the moment of inertia of that linear molecule, such as HCl. The rotational energy of a linear molecule in the z direction is this. It's mj squared h bar squared over 2I, and m sub j is equal to from negative j to positive j. Again, these two equations can be used for a linear molecule. How about nonlinear molecules? The derivation and the expressions are more complicated.